Hi everyone, this is Algebra 2, Lesson 1-6, Linear Systems. In this lesson, we'll be able to use a variety of tools to solve systems of linear equations and inequalities. The vocabularies needed for this lesson would be matrices, dimensions, inconsistent system, solution of a system of linear equations, and systems of linear equations and inequalities. Let's start with thinking about the topic. So the graph shows two lines that intersect at one point here. We already learned about solving by graphing, solving for solutions by graphing, right? So looking at this graph, what are the approximate coordinates of the point of intersection? As you can see, they're not a pretty integer, right? It's not exact. You can't really get an exact solution, but you can approximate. So what are the approximate coordinates? Yeah, anywhere between 3 and 4, but closer to 3 for x value would be a good guess. And for y value, you want it to be below 5 and greater than 4, right? So you're going to look at the two integers that your point is between, and write an approximation that best describes your point. So we can say something like 3.1 and 4.8 since it's closer to 5. Okay, but it's definitely not 3 and it's definitely not 4 or 5. So we have to approximate using decimals. Part B, how could you verify where the coordinates you estimated are, in fact, the solution? Is the point the solution to the equations of both lines? So how can you verify? Like, you have this point of approximation, right? How can we, is there a way for us to check if it's a good guess or not? Yeah, we can check if 3.1 could be one of your x value in the functions, right? If we have the equation of each line, we can plug in our values and see if they are close, and we can solve for it to compare the y values, right? So yes, we can say that the coordinates can be verified by substitution into the equation of each line. And yes, the point where the lines intersect is the solution, because that is where both x and y values will be the same in both lines, right? So by graphing, we know that this is true. So this is part B. Okay, part C. Use a result to refine your approximation and try again. Can you find the point of intersection this way? So we can approximate our equation of the line. Let's look at the y-intercepts or your points here, right? For the blue line, we can see that the y-intercept is at 3. So we can say something x plus 3. And then looking at our another exact point here, from 3, we have a 0, 3, we have 4, 5, right? So we're going up to over 4, which is 1 over 2. So 1 over 2x plus 3 would be our blue line. And for a red line, we have an exact point here, 2, 1. And we have another exact point here. That's easy to find, 6, 7. And then using 2 points, we can figure out the slope. 7 minus 1 is 6. And then 4 minus 2 is 2. So 6 over 2 is 3. So we can also see another exact point here, right? So your red line would be y equals 3x. And then we don't know the y-intercept, but we can solve for it. 1, 2, 3 over 1. So that's negative. So 1 comma negative 1. 1, 2, 3 over 1. So that is negative 3, negative 4, negative 5. So it's probably going to be negative 5. Or you can solve it algebraically. Okay? So those would be our equations of the line. And you can plug in your values. Plug in 3.1 into the first equation. And then you'll get y equals 1 over 2 times 3.1 plus 3. And then see what you get for y value. You would get 1.55 plus 3, which is going to be 4.55. So for the blue line, we get 3.1 comma 4.55, which is pretty close to 4.8. And then let's try the red line. If we have 3.1, what is our y, right? Our y would be 9.3 minus 5, so that would be 4.3. So yeah, let me write that down. And then, yeah, and then we have 3.1 comma 4.3. So we can see that our y values, if our x value is 3.1, our y values are closer to 4.5 or 3, or maybe we can say 4.4. So yeah, we can adjust our answers using algebra as well. So for part C, we can say that yes, we can use our result to refine our approximation. The answer could be obtained this way as long as the coordinates are rational. But solving algebraically may be more efficient. Yeah. So how can you find and represent solutions of systems of linear equations and inequalities? We're going to look at that. Let's look at example 1. Solve a system of linear equations. What is the solution of the system of linear equations? We have one equation that is x plus 2y equals 3, and we have another equation x minus 2y equals 4. This is called a system of linear equation, a system of linear equation. A system just means that you have more than one equation, and altogether it's a system. It's one problem, okay? So we want to find the solution of the system of linear equations. Means we're going to find a point that works for both equations. So the solution of the system of linear equation is the set of all order coordinates. So it doesn't have to be one, but it's all points, okay, that simultaneously make all equations in the system true. So algebraically, you want to figure out what x and y would be when the x values and y values are equal to each other, right? So you can rewrite your equation into slope-intercept form and substitute. That is one method. So substitution. And then we have another method called elimination for solving algebraically. We'll see that later, okay? So solve for y. Your y should equal to negative 1 over 2x plus 3 over 2, right? And then your y should equal to negative 1 over 2x, right? Or positive 1 over 2x minus 2. Yeah. The textbook solves for x because the numbers are prettier. So really, you can either solve for x or y and just make the expressions equal to each other, because the goal is to find the x and y values that are the same in both equations, right? So you're gonna set up one variable to set them equal to each other. So steps. Isolate one variable. And then the next step would be set the expressions equal to each other. Okay, so then you have, in my case, I have 1 over 2x plus 3 over 2 equals 1 over 2x minus 2. And then if you solve for x, you can just set 3 minus 2y equal to 4 plus 2y, and then you'll be able to solve for y. But in this case, I'll be able to solve for x first, and I should get something like 7 over 2. And then I substitute x into my original equation. Any equation would be fine. And then I solve for y, 7 over 2. I'm going to substitute on this one, in this one. Minus 2y would equal to 4. So if you solve for y should be 1 over 4. And then, yeah, if you solve for y first, you substitute 1 over 4 into your value. Sorry, negative 1 over 4. And then you will be able to solve for x. Okay? Yeah, so this is substitution method. You will isolate one variable and then set the expressions equal to each other, and then solve for the variable, and then you will substitute into original equation to solve for the other variable. And then you write it as a coordinate point. And that's your answer. Let's try number 1A and B. Pause the video and see if you can solve it by yourself, and you can come back when you're ready for answers. Okay, are you ready? Yeah, so let's solve the first one. You can isolate y's or x's Or you can just isolate one variable for one equation. So the first one becomes y equals negative 2x minus 1, right? So then we can substitute y into your second equation and say 5 times y, but instead of y, we're going to write negative 2x minus 1 minus 6x is equal to 7. And then we solve for x first, okay? And then I'm going to go here. Then you have negative 10x minus 5 minus 6x equals 7. Then you have negative 16x equals 12. And then you have x is equal to negative 12 over 16. But that's really 3 over 4. So x is negative 3 over 4. Right? And then you substitute your x into your y. You can use the first equation. So go back to the first equation and then substitute negative 3 over 4 minus 1. And then you will have 3 over 2 minus 1. So that is 1 over 2. So you should have negative 3 over 4, comma 1 over 2. And that should be your solution for part A. Okay? You will notice something weird for part B, right? So, yeah, this one you can solve by elimination. How that works would be matching your variables, the coefficients of your variables, and then adding all your equations together. So for example, you can make the first equation multiplied by negative 2, right? You probably learned this in Algebra 1 already, so you should know. Negative 6x, so if you multiply by negative 2, you have negative 6x minus 4y is equal to negative 10. And then we have 6x plus 4y equals 3. And then you add these two equations all together. So then x is 0x, it's gone. Y is 0y, it's gone. So then we have 0 is equal to negative 10 plus 3, which is negative 7. Is 0 equal to negative 7? This is not true, right? So if if something like this happens, it means that there is no x or y values, that x and y values that would be in both equations. So it is no solution. Okay, so you have the special solutions. Remember, if you have something like this, and then your equation is true, like 0 equals 0 and negative 7 equals negative 7. So if you get something like 0 equals 0 or negative 7 equals negative 7, then it's all real numbers. Okay? So you have special cases like all real numbers and no solution. Usually you will have 1 point. That means you have one solution, but you can also have special cases like all real numbers and no solution, okay? When all your variables are gone. That just means you have two parallel lines or you have two lines that are exactly the same. Okay. We'll continue with the next example in the next video.